This video explores easy data augmentation. Data augmentation describes applying transformations to our original labeled examples to construct new data for the training set. This has been extremely successful in images, where we can explicitly make a classifier invariant to a rotated cat by rotating an image of a cat and then having the model train on that new image. Data augmentation is seeing increased interest in natural language processing as well. This paper explores 4 augmentations that serve as a really nice baseline for this research. Most notably, these augmentations are really easy to implement, hence the name of the paper, and produce performance gains, especially in settings with less labeled data. This video explained the 4 simple augmentations explored, the results, and some ablations of applying data augmentation for text classification. This video will explain easy data augmentation techniques for boosting performance on text classification tasks. This paper is a really great baseline for exploring 4 simple to implement data augmentations for 5 different text classification datasets using an LSTM and a CNN. The emphasis on this paper is that these data augmentations are easy to implement, compared to something like back translation that requires training a neural machine translation model to go from English to French and then back to English, hoping that the returned English sentences are slightly different and are useful as added augmented examples to the dataset, or something like Conditional BERT or using generative language models to augment datasets, all which require much more overhead for data augmentation. So these are easy augmentations, and these are the 4 operations that are explored in this paper, Easy Data Augmentation. So we have this original sentence, a sad, superior human comedy played out on the back roads of life. So in synonym replacement, we randomly select a word in the sentence and then swipe it out with the synonym using a thesaurus. So sad turns into lamentable and back turns into backward. In random insertion, we randomly select an index in the sentence and we inject a word like funniness. In this case, we're already seeing how this kind of data augmentation doesn't really make much sense. I mean, already replacing back roads of life to backward roads of life doesn't make any sense, but here we have just injecting on funniness the back roads of life. So already we're starting to get a sense of why data augmentation in natural language processing is less popular than computer vision. It's really hard to define these transformations that preserve the labels and make sense for the task. So random swap is where we randomly select 2 words, swapping roads and the, so it's on roads, back the of life. And then random deletion probably makes the most sense out of this group, along with synonym replacement, where we randomly delete a word in the sentence. So in this case, comedy is deleted, and then a lot of words are deleted. That turns this sentence into this sentence. And the idea is that we would train the model on this original sentence as well as these 4 augmented sentences as well, but we're also going to chain these together to construct even more augmented examples. And this comes with all these hyperparameters like the strength of augmentation, how many to chain together, and then the ratio of augmented to original data when feeding this into the training loop of this text classifier. Before taking a closer look at the details of these augmentations and the ablations performed in this paper, this table shows the results of applying easy data augmentation. We see huge gains in the limited labeled setting, where you only have 500 labeled examples, but the gains do start to saturate out as you use the full labeled training dataset. But you still see gains at the size of 2,000 and 5,000 labeled examples for text classification using LSTMs and CNNs. So we're seeing this gain, and it's interesting because this field is relatively new, text data augmentation, and even though these augmentations that we just looked at, like random swap or random insertion, are more likely to change the class label or produce kind of a bizarre example, they're still useful for data augmentation, and we still see these huge gains, like a 4% improvement over the LSTM with the original data and then the augmented data across these 5 different text classification datasets. This table further shows where easy data augmentation stands. It's most beneficial when we have between 0 and 20% of the dataset in all cases, especially when we have a very small amount of examples, like 4,000 or 5,000 labeled examples in the full dataset, so 10% of that dataset would only be, say, 500 labeled examples. We see less of a gain when we're, say, using 10% of this pro-con dataset that has 39,000 labeled examples, where 10% is still about 4,000 labeled examples. So the trend is really that these easy data augmentations are mostly beneficial and really kind of only beneficial. You only see a very small gain as you go up and to the right with these curves using the full data set on the x-axis. that is really mostly useful for very small labeled data sets. The first hyperparameter of these easy data augmentations that we'll explore is this parameter alpha that weights the number of words changed in the original sentence as a function of the length of the sentence. Because if we have a short sentence and we do something like random deletion, we might not have any words left at all, or we might have completely destroyed the label of the original sentence. So if we have a positive labeled example of, say, a movie review or any given sentence, we want to still have the augmented example be positive as well, and this is going to be weighted as a function of the length of the original sentence, and the idea being that the longer the sentence is, or this text sequence, the paragraph or whatever, the more likely it is to be robust label-wise to these transformations. In these text classification datasets, the length of the sentences or documents, the Amazon product reviews, the Yelp restaurant reviews, or these IMDb movie reviews can vary wildly. So these are two examples from the Torch Text 0.7 IMDb dataset. So we see in this case we have this massive review compared to this where we have a very short review. So this is why we're considering this hyperparameter alpha, where we're going to see how many of these words we're going to swap or delete based on the length of the sentence. If we're going to just start deleting words in this long review, it's more likely to be class preserving than if we start deleting words in this review. So first, the authors are going to explore this alpha parameter with each of the individual easy data augmentations. So with synonym replacement, random insertion, random swap, and random deletion, we still see more gains with respect to the smaller dataset size, and it's still more robust across this alpha parameter than with the large dataset size. When we're doing synonym replacement with the full dataset, and we have this high alpha parameter that's basically saying that we're going to swap tons of words in the original sentence, we actually see performance start to degrade because we're fitting these random sentences to these class labels that's confusing the classifier. So there's this optimal range of this alpha parameter for how strong we're going to apply the augmentation. And this is the same case in these computer vision data augmentations as well. You don't want to rotate the cat so much that you've flipped it upside down, because that's not a naturally occurring image, and it's not useful for the classifier to learn to classify a cat when it's completely upside down, or truck, ship, or whatever these things are. Or cases like, say, you're doing color histogram shifts, you can do that too strongly as well. So in this case, you see that there are these optimal values of this alpha parameter. And then secondly, it varies for each augmentation. So we're going to try to construct a discrete scale custom to each of these augmentations so that we can search over an alpha that applies to all four of the different augmentations without having to search for each one individually, which would make it a more exhaustive search. The next hyperparameter of these data augmentations to consider is the ratio of the original data to the augmented data. So synonym replacement, random insertion, random deletion, as it says, they are all random. We're randomly applying these augmentations, so we can take an original sentence and then produce many different versions of it by having this random probability that determines how we sample and then augment and produce new examples. So again, in this case, the trend is that the less data we have, the more we benefit from more augmentations. So we see with only 500 labeled examples, the ratio of 16 augmented sentences to each original sentence shows a performance gain of about 2%, 2.5%, and we see that obviously with the more data you have, it saturates enormously when you go for producing extreme amounts like 16 to 32 augmented examples per original examples. But still, it's surprising to see that when you have this limited labeled setting of 500 examples, you augmented as many as 16 augmented sentences for each original example. If you're considering applying these 4 easy to implement augmentations for your text classification problem, these are the hyperparameters recommended by the authors of the paper. So alpha is determining how many words to swap given the length of the sentence, and then this is the ratio of augmented to original examples. And as you have more labeled examples, you turn down the strength of the data augmentation in this study on text classification. This t-SNE visualization shows that even though these data augmentations are kind of risky with respect to preserving the class label, they actually do a pretty good job with this pro-con dataset. So in this case, we're looking at the t-SNE dimensionality reduction into 2 dimensions of the last hidden layer of a recurrent neural network when it's doing text classification with these pro-con examples. So it's taking the sentence and then it puts it through the neural network, and then we're looking at the last hidden layer and then reduced into 2 dimensions so that we can visualize it. So these red examples are the cons, and then the greens are the pros, and then the overlap is showing the augmented examples. So these little dots are showing how the augmented examples overlap into the other class because, say, the random insertion added all these words that now made this movie review look more positive even if it was originally negative to this LSTM network. To re-emphasize, the point of this paper is to explore these easy-to-implement data augmentations. Doing things like synonym replacement or random deletion doesn't require much overhead compared to something like Conditional BERT. Conditional BERT is using the mass language modeling to essentially do the synonym replacement with a mass token, but using the context of the whole sentence, and it's conditioned by fine-tuning the BERT model on the labels so that you can guarantee that the mass language model is going to preserve the class label. So if you don't do this, then it might say the actor is bad, completely flipping the label of the original sentence. And then as shown in the torch text examples, this is obviously a longer sentence than just the actor is good. But this requires much more overhead. So even though these generative language modeling techniques are really promising for data augmentation and natural language processing, they are harder to implement and they require training this separate generative model, which might not be worthwhile if you can still get performance gains from just something like synonym replacement. Another kind of component of this story, in my view, is that the held out test set results don't really tell the full story of how data augmentation is improving these models. So you might have this data that's distributed in this kind of silly example where they're all the blue examples, the positive examples are in the top left corner and the negative examples are in the bottom right. And the blue is what we're seeing in the training set and the purple is what is in the test set, and then red is in the train set, orange is in the test set. But as we start to move into the wild, the test distribution shift might look something like this, and that's not accounted for. And there's no metric of measuring this shift in this train test kind of split because the train tests are still kind of from this one sampling distribution. So this kind of robustness that's gained by doing something like random insertion or random deletion, swapping, isn't really well measured completely on these just held out test set evaluations. So it's interesting to look at more test sets for these deep learning models that would also probably give a better indicator into how data augmentation is improving the performance of the models. So say we had a generative model like Conditional BERT, it knows this massive data set of, say, looking at all of Wikipedia or all of the internet. So it might be able to supplement the data set with some of these examples because it's seen this with this massive data set, and then it might be able to better account for distribution shift in the wild. Easy data augmentation is exploring the parameterization of how many augmentations to apply, the ratio of augmented to original data, and then the strength of the augmentations. And we might imagine a more sophisticated way of having a finer grained search over this alpha parameter for each of the augmentations of synonym replacement, random insertion, random deletion, and random swap. And a similar story has been explored in computer vision. It started out with auto augment, where you had all these transformations to images, like shearing them or applying auto contrast, and then you had this discrete scale of augmentation magnitudes, and they applied this reinforcement learning search to search this massive space and find these fine-tuned hyperparameters for each of the given data sets like ImageNet or Street View house numbers, given this massive set of augmentations. But kind of the way that story played out and why it might not be so worthwhile to do and explore this kind of fine-grained hyperparameter search for augmentations in natural language processing and text classification is the latest line of the story has just been RandAugment. And RandAugment has these two hyperparameters, n and m, n being the strength where you apply this discrete scale of augmentation for each of the transformations, like whichever scale fits the augmentation best. Obviously, it's not just the same value for each of the augmentations, like rotation and then something like translate x. And then m is just the number of these augmentations to apply in a row, and then you're randomly sampling them. And you see the same performance in ImageNet 77.6 using this much simpler search space compared to the more exhaustive auto augment search space. So it might not really be worthwhile to try to find these exact alpha parameters for each of the augmentations, and then even further as we come up with more augmentations for text datasets. These are some quick takeaways from the paper, Easy Data Augmentation. So these four simple operations, synonym replacement, random swap, random insertion, random deletion, are unlikely to help with large datasets. They're also unlikely to help with models pre-trained on massive datasets like the transfer learning and transferring from, say, BERT weights, and they're unlikely to hurt performance. Even though it might change the class labels of something like random insertion or swapping, it's unlikely to really hurt the performance of the models, and generally deep learning models are pretty robust to label noise. And then also, kind of an interesting explanation of why this works is this easy data augmentation can introduce new vocabulary through the synonym replacement or random insertion that might allow models to generalize to words in test but not train. So back to the IMDb example from torch text, the vocabulary is something like 50,000 tokens, well, depending on what tokenizer you use. But so there's this vocabulary of the train and the test sets combined, but you might not see every token in the test set in the train set, and there could be some kind of class imbalance on the token level as well. So this kind of injection could at least help the vocabulary be better covered in the training data set. So these are some of the quick takeaways from this easy data augmentation study. Thanks for watching this overview of easy data augmentation for text classification. If you're interested in exploring data augmentation for natural language processing and text classification, this is probably the best paper to start out with and apply these augmentations as a baseline for exploring other techniques, namely because they're easy to implement, and even this alpha parameter with respect to the length of the sentence, it still really doesn't incur much of a penalty with respect to hyperparameter tuning and finding the exact best value of alpha. So thanks for watching, and please subscribe to Henry AI Labs for more deep learning and AI videos.